Learning objectives. At the end of this topic, you will be able to describe the concept of probability as a theoretical approach, understand probability of the complement of an event, evaluate problems based on probability and its concepts. Introduction. In Class 9, we have learned that experimental probabilities are based on the results of actual experiments and adequate recordings of the happenings of the events. These probabilities are only estimates. For example, if we toss a coin for another 1,000 times, we may get different data, giving different probability estimates. As the number of tosses of the coin increased, the experimental probability of getting a head or tail came closer and closer to 1 by 2. The 18th century French naturalist Comte de Buffon tossed a coin 4,040 times and got 2,048 heads. The experimental probability of getting a head in this case was 2,048 over 4,040, that is 0.507. J. E. Kerrick from Britain recorded 5,067 heads in 10,000 tosses of a coin. The experimental probability of getting a head in this case was 5,067 over 10,000. That's equal to 0.5067. Statistician Carl Pearson spent some more time making 24,000 tosses of a coin. He got 12,012 heads, and thus the experimental probability of a head obtained by him was 0.5005. We can notice that as the number of tosses increases, the experimental probability of a head or a tail seems to be settling down around the number 0.5, that is 1 by 2, which is what we call the theoretical probability of getting a head or getting a tail. Probability, a theoretical approach. Let's perform some activities and observe its outcome. Activity 1. Randomly tossing the coin. We can notice that the coin can only land in one of two possible ways, either heads up or tails up. We can reasonably assume that each outcome, head or tail, is as likely to occur as the other. We refer to this by saying that the outcomes, head and tail, are equally likely. Activity 2. Throwing a die once. We can notice the outcomes are 1, 2, 3, 4, 5, 6. Each number has the same possibility of showing up, so the equally likely outcomes of throwing a die are 1, 2, 3, 4, 5, and 6. From the two activities, can we say that outcomes of all experiments are equally likely? Let's perform another activity. Suppose that a bag contains 4 red balls and 1 blue ball, and you draw a ball without looking into the bag. Since there are 4 red balls and only 1 blue ball, we are more likely to get a red ball than a blue ball. So, the outcomes, a red ball or a blue ball, are not equally likely. However, the outcome of drawing a ball of any color from the bag is equally likely. So, all experiments do not necessarily have equally likely outcomes. In Class 9, we defined the experimental or empirical probability, P of E, of an event E as shown. The assumption of equally likely outcomes, which is valid in many experiments, as in the two activities seen above, of a coin and of a die, is one such assumption that leads us to the following definition of probability of an event. The theoretical probability, also called classical probability, of an event E written as P of E is defined as shown. P of E is equal to number of trials in which the event happened over total number of trials. P of E is equal to number of outcomes favorable to E over number of all possible outcomes of the experiment, where we assume that the outcomes of the experiment are equally likely. Probability theory had its origin in the 16th century when an Italian physician and mathematician, J. Cotton, wrote the first book on the subject, the Book on Games of Chance. The study of probability has attracted the attention of great mathematicians. James Bernoulli, 1654 to 1705. A. de Moivre, 1667 to 1754, and P.A. Simon Laplace are among those who made significant contributions to this field. Laplace's Theorie Analytique des Probabilités, Laplace's book 1812, is considered to be the greatest contribution by a single person to the theory of probability. In recent years, probability has been used extensively in many areas such as biology, economics, genetics, physics, sociology, etc. Find the probability of getting a head when a coin is tossed once. Also find the probability of getting a tail. In the experiment of tossing a coin once, the number of possible outcomes is 2, head H and tail T. Let E be the event, getting a head. The number of outcomes favorable to E, that is of getting a head, is 1. Therefore, P of E is equal to P of head is equal to number of outcomes favorable to E divided by number of all possible outcomes. That's equal to 1 by 2. Similarly, if F is the event getting a tail, then P of F is equal to P of tail, that's equal to 1 by 2. A bag contains a red ball, a blue ball and a yellow ball, all the balls being of the same size. Kritika takes out a ball from the bag without looking into it. What is the probability that she takes out 1. Yellow ball, 2. Red ball, 3. Blue ball? Kritika takes out a ball from the bag without looking into it, so it is equally likely that she takes out any one of them. Let Y be the event. The ball taken out is yellow. B be the event. The ball taken out is blue. R be the event. The ball taken out is red. Now the number of possible outcomes is equal to 3. The number of outcomes favorable to the event Y is equal to 1. So, P of Y is equal to 1 over 3. Similarly, P of R is equal to 1 over 3 and P of B is equal to 1 over 3. Note 1. An event having only one outcome of the experiment is called an elementary event. In example 1, both the events E and F are elementary events. In example 2, all the three events Y, B and R are elementary events. 2. In example 1, we note that P of E plus P of F is equal to 1. In example 2, we note that P of Y plus P of R plus P of B is equal to 1. Observe that the sum of the probabilities of all the elementary events of an experiment is 1. Findings. The events E and F in the example are not elementary events because the event E has 2 outcomes and the event F has 4 outcomes. From example 1, we note that P of E plus P of F is equal to 1 by 2 plus 1 by 2, that's equal to 1, says equation 1. Where E is the event getting a head, F is the event getting a tail. From 1 and 2 of example 2, we also get P of E plus P of F is equal to 1 by 3 plus 2 by 3, that's equal to 1, says equation 2, where E is the event getting a number greater than 4 and F is the event getting a number lesser than 4. Getting a number not greater than 4 is the same as getting a number less than or equal to 4 and vice versa. In 1 and 2 above, F is the same as not E. We denote the event not E by, so P of E plus P of not E is equal to 1. That is, P of E plus P of E bar is equal to 1, which gives us P of E bar is equal to 1 minus P of E. In general, it is true that for an event E, P of E bar is equal to 1 minus P of E. The event E representing not E is called the complement of the event E. We also say that E and not E are complementary events. Before proceeding further, let's try to know about impossible and sure event by finding the answers to the following questions. 1. What is the probability of getting a number 8 in a single throw of a die? 2. What is the probability of getting a number less than 7 in a single throw of a die? Answer 1. We know there are 6 possible outcomes in a single throw of a die. 1, 2, 3, 4, 5 and 6. since no face of the die is marked 8, so there is no outcome favorable to 8. That is, the number of such outcomes is 0. In other words, getting 8 in a single throw of a die is impossible. So, P of getting 8 is equal to 0 by 6, that's equal to 0. That is, the probability of an event which is impossible to occur is 0. Such an event is called an impossible event. Answer 2. Since every face of a die is marked with a number less than 7, it is sure that we will always get a number less than 7 when it is thrown once. So the number of favorable outcomes is the same as the number of all possible outcomes, which is 6. Therefore, P of E is equal to P of getting a number less than 7 is equal to 6 over 6, that's equal to 1. So the probability of an event which is sure or certain to occur is 1. Such an event is called a sure event or a certain event. Note: from the definition of the probability P of A, we see that the numerator, number of outcomes favorable to the event E, is always less than or equal to the denominator, the number of all possible outcomes. Therefore, 0 lesser than equal to P of E lesser than or equal to 1. Let's work out some examples. An unbiased die is thrown. What is the probability of getting 1. An odd number, 2. A multiple of 3, 3. A perfect square number, 4. A number less than 4. Solution: an unbiased die is thrown. We may get 1, 2, 3, 4, 5 or 6. So total number of all possible outcomes is equal to 6. 1. Favorable outcomes for an odd number are 1, 3, 5. So number of favorable outcomes is equal to 3p of an odd number. That's equal to number of favorable outcomes over total number of possible outcomes. That's equal to 3 by 6, that's equal to 1 by 2. 2. Favorable outcomes for a multiple of 3 are 3 and 6. So, number of favorable outcomes is equal to 2p of a multiple of 3. That's equal to 2 by 6, that's equal to 1 by 3. 3. Favorable outcomes for a perfect square number are 1 and 4. So, number of favorable outcomes is equal to 2p of a perfect square number. That's equal to 2 by 6, that's equal to 1 by 3. 4. Favorable outcomes for a number less than 4 are 1, 2 and 3. So, number of favorable outcomes is equal to 3p of a number less than 4. That's equal to 3 by 6. That's equal to 1 by 2. Let's work out another example. 3 unbiased coins are tossed together. Find the probability of getting 1. All heads, 2. 2 heads, 3. 1 head, 4. At least 2 heads. Solution: when 3 unbiased coins are tossed together, possible outcomes are HHH, HHT, HTH, HTT, THH, THT, TTH, and TTT. So total number of possible outcomes is equal to 8. 1. Favorable outcome is equal to HHH. So number of favorable outcomes is equal to 1p of all heads. That's equal to number of favorable outcomes over total number of possible outcomes. That's equal to 1 by 8. 2. Favorable outcomes are HHT, THH, and HTH. So number of favorable outcomes is equal to 3p of 2 heads. That's equal to 3 by 8. 3. Favorable outcomes are HTT, THT, and TTH. So number of favorable outcomes is equal to 3p of 1 head. That's equal to 3 by 8. 4. Favorable outcomes are HHH, HHT, HTH, and THH. So number of favorable outcomes is equal to 4p of at least 2 heads. 4 by 8, that's equal to 1 by 2. Let's work out another example. Find the probability that a leap year selected at random will contain 53 Sundays. Solution: in a leap year, there are 366 days. but 366 days is equal to 52 weeks plus 2 days. Thus, a leap year has always 52 Sundays. The remaining 2 days can be 1. Sunday and Monday, 2. Monday and Tuesday, 3. Tuesday and Wednesday, 4. Wednesday and Thursday, 5. Thursday and Friday, 6. Friday and Saturday, 7. Saturday and Sunday. Clearly, there are 7 elementary events associated with this random experiment. Let E be the event that a leap year has 53 Sundays. Clearly, the event E will happen if the last 2 days of the leap year are either Sunday and Monday or Saturday and Sunday. Favorable number of elementary events is equal to 2. Required probability is equal to 2 over 7. Let's work out another example. Find the probability that the card drawn is 1. An ace, 2. Either red or king, 3. A face card, 4. A red face card. Solution. Here total number of possible outcomes is equal to 52. 1. There are 4 ace cards in a pack of 52 cards. One ace can be chosen in 4 ways. So favorable number of outcomes is equal to 4p of an ace. Number of favorable outcomes over total number of possible outcomes. That's equal to 4 over 52. That's equal to 1 over 13. 2. There are 26 red cards including 2 red kings. Also, there are 4 kings, 2 red and 2 black. Card drawn will be a red card or a king if it is any one of the 28 cards. 26 red cards and 2 black kings. So, favorable number of outcomes is equal to 28p of either red or king. That's equal to 28 over 52. That's equal to 7 over 13. 3. Kings, queens and jacks are the face cards. So favorable number of outcomes is equal to 3 into 4, that's equal to 12. P of a face card is equal to 12 over 52. That's equal to 3 over 13. 4. There are 6 red face cards, 3 each from diamonds and hearts. So favorable number of outcomes is equal to 6p of a red face card. That's equal to 6 over 52. That's equal to 3 over 26. Let's work out another example. Cards marked with the numbers 2 to 101 are placed in a box and mixed thoroughly. One card is drawn from this box. Find the probability that the number of the card is 1, an even number, 2, a number less than 14, 3, a number which is a perfect square, 4, a prime number less than 20. Solution. From 2 to 101, these are 101 minus 2 plus 1. That's equal to 100 numbers. So total number of possible outcomes is equal to 100. 1. From 2 to 101, the even numbers are 2, 4, 6 and so on up to 100, which are 50 in number. So number of favorable outcomes is equal to 50. P of an even number is equal to number of favorable outcomes by total number of possible outcomes. That's equal to 50 by 100. That's equal to 1 by 2. 2. From 2 to 101, the numbers less than 14 are 2, 3 and so on up to 13, which are 12 in number. So, number of favorable outcomes is equal to 12. P of a number less than 14 is equal to 12 by 100. That's equal to 3 by 25. 3. From 2 to 101, the perfect squares are 4, 9, 16 and so on up to 100, which are 9 in number. So, number of favorable outcomes is equal to 9. P of a number which is a perfect square is equal to 9 by 100. 4. From 2 to 101, the prime numbers less than 20 are 2, 3, 5, 7, 11, 13, 17 and 19, which are 8 in number. So, number of favorable outcomes is equal to 8. P of a prime number less than 20. That's equal to 8 by 100. That's equal to 2 by 25. Let's work out another example. Two dice are thrown simultaneously. Find the probability of getting a doublet. That is, same number on both dice. 2. The sum as a prime number. Solution. Possible outcomes associated with the random experiment of throwing two dice are: total number of possible outcomes is equal to 6 into 6. That's equal to 36. 1. The favorable outcomes are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Total number of favorable outcomes is equal to 6. So P of a doublet is equal to number of favorable outcomes by total number of possible outcomes. That's equal to 6 by 36. That's equal to 1 by 6. 2. Here, favorable sum of as a prime number are 2, 3, 5, 7 and 11. So favorable outcomes are 1, 1, 1, 2, 2, 1, 1, 4, 4, 1, 2, 3, 3, 2, 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 3, 6, 5 and 5, 6. Number of favorable outcomes is equal to 15. P of the sum as a prime number is equal to 15 over 36. That's equal to 5 over 12. Summary. Let's summarize the topic. The theoretical classical probability of an event, written as P of E, is defined as P of E is equal to number of outcomes favorable to E by number of all possible outcomes of the experiment, where we assume that the outcomes of the experiment are equally likely. The probability of a sure event or certain event is 1. The probability of an impossible event is 0. The probability of an event E is a number P of E such that 0 less than P of E less than 1. 6. An event having only one outcome is called an elementary event. The sum of the probabilities of all the elementary events of an experiment is 1.